Hi again, this is Jim Corkins, and we are continuing on with electric fields in 2 dimensions. This is 2.2. Alright, so if you haven't done the reading, please do the reading. The readings are listed right here. If you're in Physics 101 or Physics 112, please read chapters 18 in OpenStax, 15 in Survey, and 17 in Coletta. If you're in Physics 131, please read Chapter 5 in OpenStax, Chapter 26 in Night, or Chapter 17 in Coletta. And again, this is linked to the homework number 3. Alright, well, we are going to be doing the same thing that we've been doing in the last 2 chapters, which is dealing with electric fields, but now we're going to be talking about it in 2 dimensions, and specifically, what do you do when an electric field vector is not aligned to your coordinate system? Really, that's all we're doing. So we're going to be doing some trigonometry and basically taking a vector, an electric field vector, and then aligning it into the 2 dimensions. So we're going to have to solve a problem like this in which this field vector right here is pointing up and to the right. So we're going to have to, if we called this theta right here, and I'll mark this document, we'd have to create a little triangle. It's a little bit of a preview. We'd have to take this electric field vector and break it up into up and down and left and right. Okay. And so the addition of those 2 vectors creates the net field vector. Well, if this were an angle theta, this would be E cosine of theta, and it's pointing in the positive direction, and this would be E sine of theta, pointing in the upwards y direction. This would be pointing in the so the bottom right, the arrow pointing to the right here would be pointing in the positive x directions, the arrow here pointing upwards and pointing in the positive y directions. And then E would still be just KQ, this is K, by the way, this is just K, which is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. So nothing's really changed as far as an electric field. So this would just be KQ over the distance r squared. And that would be the magnitude of the E field. And that magnitude would go here as well as here. Okay. Great, my GeForce driver is available for download. Anyways, so that's pretty much what we're going to be concentrating on. All right. And to do that, let's just deal with one electric field problem in basically an electric field vector emanating from a single charge, which is in 2 dimensions. Okay. And this is a classic type of problem, and it's a problem that's also in your 2.2 electric fields 2D tutorial. So I'm going to do this one right here, and I think this is the very first. It's the top left slide, part A. It's also known as electric fields 5. Okay, so suppose you had a negative 2 Q charge here, and that negative 2 Q charge is a distance 2D up and 2D down and 3D to the right from where you're going to draw your electric field point vector. Okay, and point P is where you're going to be drawing the vector at. So right now, which way should the electric field vector at point P be pointed? Should it be pointed towards or away from the negative 2Q charge? Okay, so it should be pointed towards the negative 2Q charge. So you just draw a little vector like that, right? So the first step, like the 1-dimension problem, is drawing the electric field vector. And maybe I should just actually use the arrow that's supplied here. I'm going to use black, border black. Okay. Draw that vector here a little bit more straight than my vector. All right, so we drew the electric field vector. Now, typically in the one dimension stuff, we would just go ahead and start creating our equations from here, but we have a bit of a problem, okay? This vector right here is in 2 dimensions. It's not aligned to our coordinate system, meaning our coordinate system, which I'm going to create it right here, and I will use green. Anyways, our coordinate system here is going to be up is right, and to the right, up is in the positive y direction, to the right is in the positive x direction, and down is in the negative x direction. Okay. All right, so as you can see, we need to take this diagonal black arrow and basically put it to our 2-dimensional problem, okay? Or to our coordinate system. So when I go to do that, basically here's what I do. I kind of just describe this arrow. Well, this arrow is pointing down and to the right, okay? And I want to make this problem here, Mark has written it where he's given us distances, and I want to create a triangle. And I guess what I'm going to do is I'm going to break up that black arrow into, and I could have drawn it coming down first, but I chose to the right first, and a down arrow is blue, okay? And so you could see that whatever the name of this electric field is, so here's the electric field vector. I'm just going to give it, it's got a magnitude E for right now. So the problem with this is that I have to break this up into up and down and left and right before I create my equations, okay? And so what I'm going to do is I've made a triangle over here, and I'm going to call this angle theta, all right? I could have chosen this as theta as well, but I like to try to keep, actually, let me do that. I'm going to make this theta. We tend to always make the x direction cosine, and so by choosing this as my theta, I'm going to make this part the sine. I'm going to break with convention. Yeah, that sounds fun. Anywho, here we go. Well, now I've got my arrows, and so we know that sine of theta is equal to opposite over hypotenuse. In this case, the hypotenuse is the net electric field. And so what that means is the side opposite the angle theta is going to be E sine of theta, right? And maybe I should do this over here. So sine of theta is equal to opposite over hypotenuse. In this case, hypotenuse is the net electric field. And so that is going to be E sine of theta, which is going to be the opposite side. We know cosine of theta is equal to the adjacent side of the angle divided by the hypotenuse, which is going to be E cosine of theta. Well, which one of these two arrows, the blue or the red, is going to be the opposite side of the angle theta? What do you think? Well, the red side is going to be the opposite side of the angle theta, and so that opposite side is now going to be called E cosine of theta. Okay? And that's going to be pointed, that arrow is pointed to the right, so it's pointed in the positive x direction. Right? The blue arrow is pointed down, so it's pointed in the negative y direction. And that is going to be E sine, oh boy. I made a mistake. Oh my goodness. Let's rewind that for a second here. This should be sine. Making mistakes. There you have it. This should be E sine of theta, because sine goes with opposite. There you go. So if you were confused by that, you were right to be confused. I made a mistake. Anywho, so the side opposite the angle theta is going to be E sine of theta. And the blue arrow is adjacent to the angle theta. So this side is pointed down, so it's pointing in the negative y direction. That's why the negative is in front. And this will be cosine of theta. All right. Well, now let's go ahead and write our expression for the x component electric field at point P and the expression for the y component of the electric field at point P. Let's do that. So the x direction component for the electric field at point P is going to be E, well, I'm going to sum the electric field in the x direction, and that is simply just going to be E is pointed to the right, E sine of theta. Okay. Now the problem with this is we don't know what the electric field, we have two unknowns with this. We don't know the electric field and we don't know theta. Okay, but we have some clues, right? This distance, for theta, we could actually use the sides to figure this out. To figure out the angle theta, correct? And so if we take this all the way down, and if I were to extend this vector all the way down, so I'm going to do some erasing here. Right here. All right, so I'm extending that to make a few things a little bit easier. And this is angle theta. We could actually use the sides of this container to figure out what the angle theta is. And not only that, with the electric field, so we're going to figure out what theta is. Okay, the angle theta is using the sides, right? And we also have a problem because the magnitude of the electric field right here, so this is going to be a distance r away. So in order to figure out what the magnitude of that electric field vector is, well, we need to define what r is. We have the amount of charge, which is negative 2q, but we don't know how far point P is from where our charge is, and so that's defined as the distance r. Well, again, we're going to have to use the sides of this to figure that out. So let's figure out the angle theta first. The best way to do it is we have the angle theta here, and we have opposite and we have adjacent, right? So what I'm going to do, tangent of theta is equal to the opposite over adjacent, which in turn is basically 3D over 2D. And the D's are going to cancel out. And so that's just 3 over 2. So theta, what we could say here, I'll erase this. What we could say theta is going to be the inverse tangent of 3 over 2. And so in my case, the inverse tangent of 3 over 2, let me get my little handy dandy calculator here, 3 divided by 2 equals, and then I need to do trigonometry, and I need to do the inverse tangent of 1.5, which is 56.31 degrees. So this is going to be 56.31 degrees. Okay, cool. So we figured out that part of the unknown. Now we have to figure out what the electric field is. The electric field is going to be, and this is just the magnitude of this right here. So this side of the electric field is the net electric field, okay, which is the hypotenuse, but it's also distance r, right? So so we're just finding out the net electric field, which is going to be K and times a negative 2Q, and that's capital Q, all over the distance r squared, right? But r, so I'm going to write this out, K negative 2Q. But in this case, how do we get what r is? Well, r, right here, this distance r, isn't r just going to be c squared equals a squared plus, this is c squared, isn't that just a squared plus b squared square rooted? Right? So r squared is going to be equal to 3d squared plus 2d that you're going to square. So overall, this is going to be 3d squared, so that's going to be 9d squared plus 4d squared. So 9 plus 4 is what was that, 13d squared? So r is going to be actually equal to 13d squared. Well, the square root of, so r is going to be equal to d square root of 13. Well, this is already r squared on the bottom, so don't put r in and then square it, because you'll just be squaring the square root. So suffice to say is just go ahead and put your 13d squared here. Since r squared is equal to 13d squared, just write it in here. And so overall, the magnitude of the net electric field is just going to be 2kq over 13d squared. So it's going to be 2/13 d squared, which is what number 3 is asking. So this is, we just did number 3 here to get this. Well, now we could actually sub in our theta. Now we got this magnitude right here. So that electric field in the x direction, the electric field in the x direction is going to be the magnitude of the net electric field sine of theta. So that's going to be 2/13 kq over d squared sine of 56.31 degrees. And this is going to be number 1. To get number 2, we're going to have to sum, we're going to have to do the same thing for the y direction, except in the y direction, the magnitude of that electric field is going to be pointed down, and it's going to be cosine of theta. Well, that's going to be negative 2/13. I brought the negative down here, which is going to be kq over d squared cosine of 56.31 degrees. And this is going to be number 2. So to get number 4, the overall direction of this electric field is going to be pointed down and right. By the way, we chose a different angle for ours. So this is basically 57 plus, 56.31 plus 33.7 is 90 degrees. So we just chose a different angle than their theta. Mark would have chosen this to be the angle theta. I chose angle theta to be here to be a little bit different, but the answer here works out to be 1.54 kq over d squared, and the answer for the y direction works out to be that. So this is the overall basics of how to break up an electric field in the x and y direction. Note that they both have the same magnitude, right? If E is defined as the hypotenuse, this is just, and then we have evaluated E to be 2/13 kq over d squared, then the red arrow pointing to the right is going to be pointed positive 2/13 kq over d squared sine of 56 degrees. And it's going to have the same hypotenuse as the y direction stuff, except this will be pointed down. And so the only difference between the x and y direction, I guess is what I'm saying, is the angles, right? So when you're doing these problems and you're writing your diagonals, if this magnitude here is different from this magnitude here, then you've made a mistake. The only difference between the x direction and y direction component is basically the sines and cosines. Okay? All right. Let's get a little bit more complicated. We're going to add an electric field. We're going to add 2 charges, and we're going to have to do 2 diagonals in 2 dimensions. But before we do that, let's go ahead and talk about what is a dipole. We talked about a little bit what a dipole is the last time when we were talking about 1-dimension stuff. Okay, so it's really important to talk about what is a dipole. So what is a dipole here? So a dipole is basically anything that has 2 charges on it. Okay, so in this case, and usually when you talk about a dipole, you're talking about a negative charge and a positive charge, right? Sometimes we would, the Earth has we talk about dipoles with magnetism like north and south, right? So typically when you talk about dipole, it's the opposites, right? But you could have 2 positive charges, and that is the same thing as a dipole. It's just 2 point charge, so you could actually, I've heard it referred to as a dipole as just 2 point charges, right? But really, when I think of a dipole, it's actually 2 point charges of the same magnitude, but in opposite directions, okay? And they're a very short distance apart. You're talking about the atomic scale here, okay? So the dipole is, a hydrogen atom, for example, would be considered a kind of a dipole. It's got a negative on top and 2 positive so this water atom is a dipole of sorts. It's got a negative on top and 2 positives on the bottom. So you could just call that a positive 2 Q here, and then a negative 1 Q up here, right? So you would just call the bottom as a 2Q magnitude. A single charge has 2 protons, so it'd be 2 times 1 1.6 times 10 to the negative 19th coulombs. And it's positive. In the top, it would just be negative 1.6 times 10 to the negative 19th coulombs, and which is just one negative charge, right? So this, you could consider a water atom as having a single positive charge. It has just has twice the amount of charge on it than the top one. So that's kind of why some people refer to a water atom as a dipole. Okay. The product of the charges. So basically, this is going to work out to be like a kind of a torque problem. So typically, these poles are separated by a distance d. So in this case, it's going to be separated by a distance d. Right? And you have two charges, and this is called the moment, right? Okay. So this dipole moment is you've probably run into this into your chemistry class, is basically the units, and it's not, I know it's got a P here, all right, and that's not momentum, it's moment, okay, and it's kind of a electric polarity thing, and so its units are in coulomb and meters, okay. So basically, the further these charges go are spread out, okay. Okay, so if you spread these charges out, increase this distance that the charges are spread out, the electric dipole moment is going to increase over time. Okay, and basically it's basically a way just to measure, to really quickly measure the separation distance between charges. Okay, and it will play in later on to the reason why you hear moment, and typically when you hear the term moment, that you think of torque, or I think of torque, right? It's what engineers and chemists call is a torque. So it's going to be playing into force in spinning these guys, and so how these charges can actually spin, right? And what their overall electric field is at various points, and it has to do with also valence bonds as well. All right. So I wanted to take a moment and talk about the electric dipole moment. Okay. But dipoles are important because we're going to be doing problems where you have, where we're going to be calculating the electric field at point P. And then later on, you could actually use that to calculate the torque. If you placed another charge right here at point P, how that would torque or cause this entire atom right here to begin its spinning. Okay? So, there's also some cool tricks we could do to do this as well. All right. So cool math tricks to calculate the electric field. So what we would do in order to calculate that torque, you would have to use a dipole moment. But what we do is we'd have to place a charge here at point P that would cause this thing to begin to spin, or spin clockwise or counterclockwise, depending on the charge that we place at point P. And that charge that we place at point P is going to interact with this electric field at this point right here. And it's going to not only cause this to spin, but this is going to have like a center of mass thing. So it's actually going to pull and push these guys as well. So it's going to start spinning about a center of mass. Okay. Anyways, so this is a cool problem to do. All right. While we're here, let's practice let's practice this problem. You have a negative charge up here, so this is going to be a negative Q1 up here, and it's going to be a positive Q2 down here. And they're separated by a distance, well, this is a distance positive y, this is distance 0, and this is distance negative y. and y is equal to y. So basically they're distance separated. Their separation distance, which dipole moment was q and d, right? So we have basically two of these q's, and we want to do a magnitude here. So it would be 2 q's, and each q is 1.6 times 10 to the negative 19th. And then so they're a distance 2 y's apart. So that's how you would calculate that dipole moment. It would be 1.6 times 10 to the negative 19th coulombs, and times whatever y is. Y could be usually it's in a nanometers is what they would be typically measured in, like an angstrom or something, okay? Anyways, so what we have to do here is basically concentrate on the electric field. So let's get away from calculating electric dipole moments and talk about the electric field. Because the electric field interacting with whatever charge, the electric field at point P interacting with whatever charge you place at point P is going to cause that force. And then it's going to cause a dipole moment and the spinning and things like that. All right. So you have a negative Q1 up here. You have a positive Q2 up here. So the electric field is going to be pointing up and towards that negative Q1. So that's what we're going to call E1. And it looks like it's been given as a distance d away. All right. And we're going to have another electric field that is going to be pointed up and away from this positive charge, right? The electric field is pointed away from that positive charge. So that's going to be pointed an equal amount. And that electric field is going to be called E2. Okay? And it's also a distance d apart. Now, if we're taking the magnitudes of these, and E1 is going to be equal to K and Q1, which is a positive Q1, all divided by a distance apart squared, and the magnitude of E2, actually I want to go ahead and put this around this, so this, put the absolute values around that. So E1 is actually going to be just K Q1 over D squared. E2, the magnitude of E2 is going to be K and the negative Q2 all over D. So that point P is a distance d away from Q2, which is causing this electric field up and away. And so that is going to be K Q2 over D squared, right? Well, if the magnitude of Q1 is equal to the magnitude of Q2, can't we say that the magnitude of E1 is going to be equal to the magnitude of E2? Right? So we're kind of leading in, kind of analyzing information, right? In the addition of vectors of E1 and E2, I don't know why I put, these should be vectors, put magnitudes on them. These should be vectors. Anywho, well, if you add vector E1 to E2, you got up and to the left plus up and to the right an equal amount. Well, the net part of that, E1, E2, which is E net, is going to be just pointed straight up. Okay? So what I'm doing is I'm basically just kind of looking at some information to figure out what the overall net direction of the electric field should be, right? because it's starting to look like E2 is pointed to the right and is pointed up. I'm going to have to draw a triangle at some point, so I'm going to move E2 to the top part of this triangle. And if this is the angle theta, then this is the angle theta, right? And this side of it is going to be E2 cosine of theta, and the top part is going to be E2 sine of theta. And it's pointed up, and this is pointed to the right. Well, this guy is also forming a vector. And E1, I'm going to actually rewrite this as in a blue color. To differentiate this. Just make sure so you know what I'm talking about, how E net is different. E net, I'm going to call red. E2 is black. All right. Anyways, the arrow pointing to the left of E1 is going to be E1. It's going to be negative E1 cosine of theta. And the arrow pointed up of E1 is going to be positive E1 sine of theta. All right? Well, since E1 is equal to E2, let me use pink for this next part. If E1 is equal to E2, let's just call that E, distance E, where E is equal to KQ over D squared. Okay? Equal to KQ over D squared. All right, because if Q1 is equal to Q2, and we'll call that equal to Q, well then E1 has got to be equal to E2, which is equal to E, and E is going to be containing Q, which is equal to Q1 and Q2. My whole point is this. This becomes a pretty simple problem, right? If you sum the electric field in the x direction here now, okay, we sum the electric field in the x direction. It's almost unimportant to do that because you have an arrow to the left that's canceling out the arrow to the right. You have you have E2 cosine of theta, and then you have minus E1 cosine of theta. But since everything's the same in here, this is going to be 0. So the only important part to sum up is the y direction stuff, which is actually going to end up being just the net direction, right? The y direction stuff is going to be E2 sine of theta minus E2, well, plus E2 sine of theta. which is going to, I mean E1 sine of theta. That should be E1 sine of theta. And since E1 is equal to E2, that's just that's just 2E sine of theta. 2E sine of theta, where E is equal to KQ over D squared. So that's going to be 2KQ over D squared sine of theta, right? And this is actually going to be, if we try to get the net, E net is going to be equal to the square root of E in the x direction squared plus E in the y direction squared. Well, E in the x direction squared is going to be equal to 0 squared, and the y direction squared is going to be 2KQ over D sine of theta squared, and then you're going to take a square root of that. So E net is going to be actually equal to 2KQ over D squared sine of theta. So that's kind of the thought process, is you're doing the same thing that we did in this last problem. Let me zoom back out. In this last problem that we did, but now we're just doing it twice. And the cool thing about this, often when we do these problems, one of these, like typically the x direction will cancel out or the y direction will cancel out, right? And so you get a chance to just really quickly eliminate stuff. And the only way the x direction cancels out in this case is because these two charges happen to have the same magnitude, right? So if they weren't the same magnitude, then KQ1 over D squared would not be equal to KQ2 over D squared. But since they're both equal, that means that, and let's set them both equal to Q, then that means the electric fields are both equal, and then now in the y direction you just have 2KQ over D squared. So, pretty cool. All right, well, let's do one last problem, okay? And this is a very similar problem, but what do you do when a dipole, when you're measuring the electric field due to a dipole not at the center? This last one, the P point, would be right at the center of the dipole. Like here, this is the x direction one. But this one is kind of off center, okay? So this is going to be a little bit easier problem. However, you're not going to get this nice clean situation where the electric field in the x direction cancels out. You're going to have both an electric field in the x direction and y direction. So let's get started. The procedure, again, the procedure that we learned in 2.0 and 2.1 is you draw the electric field due to both charges. So I'm going to call the positive charge red, and I'm going to call the negative charge blue. Okay, but Q is equal to Q, so they're the same magnitude. Okay, so the blue charge, so at point P, what do you think the blue charge's electric field will be directed? Towards or away from the blue charge? So the electric field at point P, let's draw the field vector. Which way it will be pointed? Towards or away from that negative charge? It'll be pointed towards that negative charge. And so this is the electric field due to the negative Q, capital Q. All right? and that's the vector. The red charge is going to have an electric field pointed directly away from it. And I'm thinking this is P is further away from that negative Q. So this is going to be a little bit larger since the red is a little bit closer. So that this is going to be the vector due to the positive Q. And that's a capital Q. All right. Well, the very first problem we did, we added that one single vector that didn't align with our coordinate system. So our coordinate system is going to be up and down and left and right. And I'm going to draw it through point P. Okay. And I think what I'm going to do is I am going to, again, break with a little bit of tradition. I'm sure Mark is going to say something that this is the angle theta, but I think I want to choose this as my angle theta for this. So I'm going to put this E1, this E2, this negative Q right here. All right. And we need to figure out, so a couple things that we need, so we're going to have to define what theta is, all right? Okay. So this is a distance 2d, and this is a distance d, right? And this part of the arrow, we're going to break up this hypotenuse into up and down and left and right. Okay. Okay. So actually, let me do that with vectors. I'm going to draw this arrow here. And oh. The up vector is going to be negative, so it's going to be the up vector. And that up vector is going to be the hypotenuse, negative Q, and at this point it's only the magnitude, cosine of theta, and is pointed in the positive direction. Actually, let me rewrite that and give myself a little bit of space. So this is going to be pointed up, and it's E positive Q, cosine of theta, or sine of theta rather, it's pointed opposite, this side is opposite theta. In the x direction, the x direction vector is pointed to the right in the positive x direction. And this is going to be pointed to the right, so it's in the positive x direction, and that would be the hypotenuse, or that should be a negative there, should be negative Q cosine of theta. All right. So we have some things that we need to figure out here. Okay. So the next step is we're going to go ahead and sum the vectors in the x direction. So the electric field in the x direction, I only see one arrow pointed to the right. And I like to let my equations tell me what my unknowns are. So if I haven't answered this distance d away from this guy, from point P to the negative Q, and this distance from here to here, I'm letting my equations tell me what to do. Okay? So in the x direction, I have only this vector pointed to the right, and that is going to be E due to the negative q cosine of theta. All right, and that's the magnitude of that. Well, the problem with this is we don't know what E is. We haven't defined what the electric field is at this point, the magnitude of that electric field due to the negative q up here, and we don't know what theta is. So we don't know what theta is, and we don't know what this is. So we need to define that. We need to define both of those. Okay, well, to get theta, this distance is 2d, this distance is distance d. So again, to get what theta is, I'm going to go ahead and call theta, tangent of theta is going to be equal to, tangent of theta is opposite over adjacent, so that would be 2d over distance d, 2d over distance d, and the d's cancel out, which is just equal to 2. So theta is going to be the inverse tangent of 2, which is, and I'm going to use my handy dandy calculator here. If I do 2 in trigonometry, second function, inverse tangent, that is going to be 63.43 degrees. 63.43 degrees. Well, now we know what theta is. All right. Now we need to figure out the distance from, well, actually, let's start writing this equation out. And this equation is going to be positive, and it's going to be k due to the negative q all over how far the negative q is from the distance d. Well, that's going to be kind of complicated. So, well, let's just go ahead and finish writing cosine of 63.4 degrees. Anyways, we have to figure out the distance that negative q is from the point P. Well, that distance is going to be c, so c is going to be equal to, that's c squared equals a squared plus b squared, so c squared here is the distance between point P to negative q, and that's equal to a squared, which is going to be 2d squared, plus d squared, which is just going to be d squared. So c squared is going to be equal to 4d squared plus 1d squared. That's going to be 5d squared. All right. So this is going to be a distance 5d squared, because it's the distance apart squared. Rather than take the square root of that and then square it, just leave it like this. It's much easier. So you could say that the electric field in the x direction is, and we're going to answer number 1, is going to be positive. I'm going to multiply this out. 1/5 k capital Q over d squared cosine of 63.43 degrees. All right. By doing that, we actually helped out doing the y direction stuff. In the y direction, we're going to have the up arrow here, which is going to be E negative Q sine of theta, and that's pointed up, plus the downward, oh, actually that's going to be minus, because that arrow is pointed down. So that's going to be E, and it's just positive Q without any sines or cosines, right? Because this is just pointing along in the y direction. Well, let's go ahead and define that stuff. Well, like I said before, the magnitude right here, this thing right here, is the magnitude E negative Q. So E negative Q is 1/5 KQ over D squared. So by figuring that out, we've actually figured out the magnitude here. So that's going to be pointed up, and that's going to be 1/5 KQ over D squared. Actually, it's a negative Q in here. And that's going to be sine of 63.4 degrees. Now let's do the red part, guy. That is going to be minus, this is pointed down, away from the positive Q up here. And that red electric field vector is caused by the positive Q, so that's why I'm putting the positive. And how far is point P from this Q? Well, it's a distance 2D away. So I'm going to put 2D, and then you have to square it. And there is no sine or cosine. So now merging these two equations together, I'm going to have 1/5 KQ D squared. Actually, I'm going to need some room, I think. That's going to be 1/5. I'm carrying the math over here. KQ over D squared sine of 63.4 degrees minus KQ, and I'm multiplying this all out, and 2D squared is going to be 4D squared. So this is like a 1/4 KQ over D squared. In fact, I'm going to pull out the KQ over D squared. So this is going to work out to be KQ over D squared. That's going to be 1/5 sine of 63.43 minus 1/4. Okay, well, this is our answer for the y direction. So this is actually number 2. Number 3, we worked out to be, number 3 is just the net electric field. All right. And the net electric field, we're going to probably need a little bit more room. Let me grab a whiteboard here. So I'm going to grab a screenshot of this real quick. I'm going to copy this to a whiteboard because we're going to need to do the net electric field. Let's do a whiteboard right here. So we're continuing on with this. We have to do part 3, and this is write an expression for the magnitude, the overall magnitude of the electric field at point P. So basically we have to do the net electric field, which is going to be the red arrow down and this arrow. Well, to get the net, like we did before, to get the net, to sum on the net, you got to go, that's going to be equal to the square root of E in the x direction plus E in the y direction. Okay? Well, E in the x direction here we wrote as this, which incidentally is this part, and the y direction stuff is just this part. And again, our angle's different from his because Mark chose this as his angle instead of this. Anyways, to get the overall net part, which this is net, we're going to write our expression for the x direction, which is going to be huge. All right. So the x direction stuff is going to be 1/5 kq over d squared cosine of 63 cosine of 63.43 degrees, and you're going to put it, actually let's erase this a little bit, let's make this bigger looking. So the x direction, I'm going to put it in brackets actually, it's going to be 1/5 kq over d squared cosine of 63.43 degrees squared plus brackets. Now we're going to do the y direction one. The y direction one we wrote to be this, which is going to be kq over d squared, and we have parentheses inside a bracket, so that's going to be 1/5 sine of 63.43 degrees minus 1/4 end bracket, so that's in here, and we're going to then square this part. So really, inside this bracket, the x direction is this, which is going to be 0.114 kq over d squared. That's the x direction. And the y direction is going to be negative 0.7, is going to actually just be 0.0711 kq over d squared, right? So 0.114 times 0.114, that's 0.0129. Actually, I'm going to pull the kq out. We'd have kq over d squared, and that is going to be square rooted over 0.0129 plus 0.0711 times 0.0711 equals 0.0051, which is going to be a really small number, plus 0.0129, and then we're going to square root this, which is going to be 0.134. So this overall in the net direction is going to be 0.134 kq over d squared. So this is number 3, and that's the magnitude of the overall electric field. And that overall electric field now, to get the direction of the overall electric field, we're going to take the up arrow, up and to the right. Actually, let's take the down arrow. So we're going to do number 4, which is to find the overall direction of the electric field at point P, which from here you could see is going to be pointed down and to the right. But let's go ahead and use our vectors to tell us, okay? So I have the red vector. I'm going to point down here. And then the blue vector is going to be a little bit shorter because the red vector is closer to point P. And again, this is point P right here. So the net electric field is going to be down and to the right. And so this is the net electric field. Okay? And this is going to be, oops, E negative Q. And this is going to be E positive Q. Right? So here's your example of how to do something where you have two charges off center from the data point, and I'll zoom in on this. Oops. Two charges point off center. So I'd put a data point right here in the center, is where the other problem was, but this one is off center. And so you have one diagonal, right? So we drew that, and then we drew the other vector. Then we broke the one diagonal into up and down and left and right. And then we started defining our electric field in the x direction, and that led us what our unknowns were. And we had to then define the overall net of E negative Q, and define that in terms of D. And then that led us to figure out what theta was. And so that helped us out when we were doing the y direction part, because then in defining E negative Q, we actually defined the thing here. And then we found out what theta is. And then all we were left to do in the y direction is figure out what the positive Q electric field was, which we defined as this. And then we went and solved the problem. Okay. Problems will ask for the net electric field, and know that you're going to have to, that's c squared equals a squared plus b squared, which is just going to be the square root of the x direction and y direction stuff. Okay? And so there you go. Well, I hope you enjoyed 2.2. Thank you.